Good morning and welcome to this tutorial. Now, we're going to go back to our last study, which is on momentum. And from the last study, we learned that momentum is equal to mass times velocity, meaning that objects that have mass and velocity have momentum. Now, if you have two objects, let's say, that are traveling towards each other, either in the same direction or from opposite direction toward each other, and they collide, what happens to the momentum of these two objects? According to the law of conservation of momentum, it states here that the momentum before collision of the system equals to the momentum after the collision. So the momentum of these two objects before colliding should be equal to their total momentum after colliding. So how many types of collision are there? There are two types of collision. Okay, we have elastic collision. In elastic collision, the kinetic energy is conserved. In inelastic collision, the kinetic energy is not conserved. And so we'll look further at these two. Now note that we also said that in the last lesson we've identified that momentum is a vector quantity, and that is due to the velocity. Velocity is a vector quantity. And so momentum is a vector quantity. So when we solve problems in momentum, we also take into account the vector properties. Okay, now let's look at elastic collision. The keywords indicating that the type of collision is an elastic collision can be indicated by these words. Any indication by bouncing apart, moving apart, moved away, anything that indicates that they're moving in opposite direction and they are not sticking together indicates automatically that the type of collision is an elastic collision. And because energy is conserved, they still have the energy to bounce off each other. And so we call that an elastic collision. Now, the law of momentum states that momentum before collision equals to the momentum after collision. And so to find the total momentum before collision and the total momentum after collision, we use this formula. So we'll look individually at their momentum. So let's say we have object A that has mass m, initial velocity moving at UA. Then we have object B, mass of m, moving towards object A at an initial velocity of UB. U indicates that it's in initial velocity. A and B indicate simply because it belongs to each of those two objects, masses. And so the total momentum before collision will be the sum of their momentum. So we have momentum, since we know it's equal to mass times velocity, the momentum of object A will be mass of object A times the initial velocity of object A plus mass of object B times the initial velocity of object B. And that should equal to, here we still have their masses, MA, MB. Okay? And this time after the collision, object A moved back this way and object B moved in that direction. They moved apart in opposite directions. Okay, so now we have VA and we have VB. Note that we're just drawing the vectors not to show which direction they would turn, the magnitude of the velocity, but for now the vector only indicates that they're moving apart. Okay, and the size of the vector will depend on the magnitude of their velocities after the collision. So now the momentum after collision, we have mass of object A times the final velocity of object A plus mass of object B times the velocity of object B. So this is called the general formula. Okay, it's called the general formula. Take note, I said that momentum is a vector quantity because velocity is a vector quantity. And therefore, if we were to rewrite this equation based on the vector, our equation would be ma ua minus mb ub. Now this minus is because this is in towards left, which is negative. So the velocity will be minus ub times m, which is a minus here. Okay? And that should equal to, now this time, the velocity here is going to the left. So it will be a minus MAVA plus MBVB. So these negative signs indicate the direction of the velocity. Okay? And we're going to calculate the total sum. So when you have the values, you plug the values in, and then you should be able to calculate the momentum either before or after collision or any other variables that you are asked to solve for. Okay, so this is using a vector quantity. So take note that the momentum is a vector quantity, and so the signs will change according to the direction. Now here we have the sum. The general formula indicates the sum, but because this is traveling in the opposite direction, we have mass times minus the direction there, whatever the value will be, and so you will have this as a negative. Okay, so we'll take an example now. Okay, so let's take an example. Let's say we have object A that's traveling towards B and to the right, 20 meters per second, and we have object B that's traveling to the left at 10 meters per second. Now, both objects have the same mass, 5 kilogram. After collision, they both move apart, and we have object A that's traveling to the left at 5 meters per second. What is the velocity of object B? So we're going to calculate it. So to do that, again, the law of conservation of energy says that momentum before collision is equal to the momentum after collision. Now make this a habit to write it down so it's easier for you to follow through. So before collision, the general formula is MAUA plus MBUB is equal to MAVA plus MBVB. We're solving for VB, so what we do is we put in the values. So we have 5 times 20 plus 5 times, now this is traveling to the left, so it's a minus 10 meters per second, and that should equal to, this object is now traveling to the left, so we have 5 times minus 5 plus 5 times VB, which we do not know. So note here, 5 times 20 gives us 100, and we have 5 times minus 10, which is minus 50, and that should equal to 5 times minus 5 is minus 25 plus 5 VB. Okay, so we have that. Let's go on with the arithmetics. 100 minus 50 is 50, and that should equal to minus 25 plus 5 VB. We're solving for VB, so we plus 25 to the other side. 25 plus 50 gives us 75, and that should now equal to 5 VB. We're solving for the velocity of object B, so to make B on its own, we divide by 5. Therefore, VB equals to 75 divided by 5. And what is 75 divided by 5? So we have 75 divided by 5, and so we have 15 meters per second. So come back here, note that this is 5 meters, VB is 15, and so the length of the arrow must also indicate that it is traveling faster than this. Okay, object A. So now we have solved for this. Velocity of object B after collision is 15 meters per second. And we're going to go back and prove that the total momentum before and after collision are equal. Okay, so we'll prove that now that we know that the velocity of object B after collision is 15 meters per second. Okay, so we have this. Let's put in the values in here. So this is 5 times 20 minus 5 times 10. Remember, it's to the left, so I put the minus there. And that should be equal, that's traveling to the left, so minus 5 times 5 and plus 5 times 15. So altogether, we have 100 minus 50, and that should equal to minus 25 plus 75. So here we should have 50 minus 25 plus 75 is also equal to 50. So momentum is conserved. Momentum before and after collision is conserved, and this is for an elastic collision. Now we'll look at momentum, inelastic collision. Now the keyword indicators of inelastic collision, any word that indicates that they're joined together, coupled together, or they stick together, anything indicating they went somewhere together, all right, is an indicator that it's an inelastic collision. Okay, and again, LCM basically law of conservation of momentum. Momentum before collision is equal to momentum after collision. So again, let's say we have a look at these two objects, object A and object B, mass A, mass B, and they are traveling towards each other. So we have UA, UB, okay, and as they travel toward each other, they collided. Now this time when they collided, they didn't bounce apart, but they stick together. So now we have object A, object B, they stuck together and they are now moving together in one direction. So we have A and B, and let's assume that they're both moving in that direction. Okay, for now I'm saying we assume, it depends on our calculation. So they're both now coupled together and they're both moving in the same direction. So to solve inelastic momentum, we still apply the same law, and this time we looked at the system of momentum before collision and after collision. Before collision, they're separate. So we have MA UA plus MB UB, and that should equal to them together. Now here, they're both stuck together and they're moving together, so their masses will now be added together, and they will both have a common velocity. And so the formula will be MA plus MB times their common velocity, or their final velocity together. Okay, so this is the general formula for inelastic collision. Let's give some values and do some math and calculate. For example, let's calculate the velocity of these objects after collision. Okay, so we'll use the initial values that we have used for the other example. UA will be at 20 meters per second, and UB will be at 10 meters per second, both having identical masses, 5 kilograms. And we don't know what this is, so we're calculating for their final velocity. And so we substitute the values in these equations. we have mass times 20 plus 5 times minus 10, and that should equal to mass of object A, which is 5, plus mass of object B times VF, which is the final velocity.